Boolean logic turns out to be very easy on this B tree that we've just constructed. Let's take some examples. Term 1 or term 2. Well, this is really quite easy. We'll get a lookup of term 1 in that B tree. We get a list of doc IDs. We do a lookup of term 2 in that B tree. We get a list of doc IDs. And if we feel the need to remove duplicates, we can merge these two lists because they're already in sorted order. And it's easy to merge them in a merge join style fashion. If we have term 1 and term 2, that's the intersection of the two postings lists. And here, definitely, we would want to merge them in order to find those things that are in both postings lists. The postings lists are sorted by doc ID. So this is a direct merge join of those two postings lists. And that just gives us for term 1 and term 2, the list of documents that have both. Term 1 and not term 2 is basically the same query. We're going to do a lookup on term 1. Then we're going to do a lookup on term 2. And we take the postings lists of term 1 and we look for occurrences of term 1 that are not in the list for term 2. So it's a merge again of these sorted doc ID lists. But here the rules for what we keep are it has to be in the first list and not in the second list. Now, final example you might want to answer, term 1 or not term 2. That's the union of term 1's query, which we can find by looking in the B tree and looking up term 1, and not term 2. Unfortunately, what is not term 2? It's the entire corpus minus the docs that contain term 2. That's a very big set, and there's no easy way to pull it out of our index. So that's a lot of work, and it's a huge answer. And so generally, information retrieval systems will forbid this query. They'll say, hey, you can't do a lookup that's going to fetch almost all the data in the database. And so they'll simply forbid the query. You can try it in your favorite search engine if you like. Having seen that simple introduction to Boolean search, we can actually cast the whole thing in SQL if we want to. It's a bit of an exercise. You would not want to do this. It's not efficient. But it's a way for us to think about what we just talked about in the previous slide using a language that's familiar to us in this class. And so here's a query that searches for Berkeley database research. And we're basically doing a self-join, if you will, of the inverted file table, once for Berkeley, once for database, and once for research. IB, the Berkeley instantiation of the file, right? Alias IB is where IB.term equals Berkeley. The database version, ID, is where ID.term equals database. And IR is IR.term equals research. And of course, the simple query plan for here is an index scan, where you do an index lookup for IB, you get the postings list for Berkeley. You do an index lookup for ID, you get the postings list for database. You do an index lookup for IR, you get the postings list for research. And then you simply do the joins that join those postings lists together. Now, why is it a join and not an intersection? Well, it turns out in this case, they are equivalent. Why is that? It's because each doc ID occurs at most once in each postings list. There's no pairs or duplicates here when we do the join. And as a result, we're only going to get one match for every pair. And so when we do a join, we effectively get the intersection. So here's the query plan that corresponds with the discussion in the previous slide. And then we picked a particular ordering of these lookups, which may or may not be optimal, actually. But this is how we merge them together. And we can do this as a streaming merge join of the index scan. And so when we say get next at the top of this query plan, we can actually do incremental work in each of the leaves in order to produce one answer at the root. And this is going to allow us, for example, to produce a page full of only 10 answers, let's say, without running this query to completion. Now, we can have more Boolean connectors. We can have a more complicated query simply by working out a sort of more complicated SQL query. So here's an example on the left. We're going to get window and glass or door and not Microsoft, the example we had before. I will leave it to you to read the SQL on the left that corresponds to it. But again, it's just a Boolean query on each leaf node followed by merge joins, or in the case of and not, a merge anti-join. An anti-join is where you get everything on the left that does not have a match on the right. And so it's pretty straightforward. You get these kind of merge join patterns over the terms of your query every time. And that's why I said that there's really only one SQL query template that runs at Boolean Search. In essence, the only query you ever run is a pile of merge joins over a pile of index lookups. The leaves are always index lookups on keywords. The joins are always merge joins of postings lists. And everything in your system that you build when you do text search is to optimize this one single query and make it go really fast. Okay? So the query processing basis of text search is very patterned. It's very straightforward. It's much narrower and more specific than the full set of queries we can ask in SQL. Finally, at the top of this query, we have in the SQL on the left, order by magic rank. That's my term for saying, look, the output of this thing has to be sorted in a way where the most interesting answers go out first. And that magic ranking function is the secret sauce of every text index, every search engine. And it usually uses some combination of statistics and linguistics and graph theory tricks to give you good answers. We'll study a bit of this a few slides down.